So good morning, everyone. We'll continue on from where we left off. We did KCL, KVL. Today, I want to cover the material for homeworks 3, 4, and 5. Okay. There was a specific problem in homework 2, KVL. It's about the points VAB, VCD, BBC that some students might have an issue. So I'll go over that problem in just a little while. And then if you had any issues, you send me an email, and then I'll adjust the credit online. Okay. So let's bring up. Okay. All right. So what I want to begin with today is sources, loads, and current. Actually, sources, components, not current. So circuit analysis, right? Typically, this is what I do at the beginning of the first day of class. What is circuit analysis? Well, circuit analysis is the theoretical analysis that we perform to find the unknown quantities in a circuit, okay, in an electrical circuit. So the unknown quantities are voltage, current, and then power and energy. Okay, voltage, current, power, and energy. Primarily just voltage and current, because once you have voltage and current in a circuit, you can find the power and then you can calculate the energy. So circuit analysis is basically theoretical analysis, theoretical calculations to determine the unknown voltages and unknown currents that would be present in a circuit. Now, a circuit comprises of many components. The components that we will look at in this class: resistors, capacitors, and inductors. Resistance, capacitance, and inductance is the specific quality, or not quality, quantity that is associated with these components. Okay. And of course, in your prereq physics classes, you have studied all of these, but we'll go a little bit more in depth than your physics classes. Okay. So resistors, inductances, and capacitances are the three components that we'll look at in this class. All of these can be classified as loads. So load. Okay. And then you have sources that provide energy, sources that provide electrical energy. And sources would provide voltage and current, both. Okay. So again, in a typical electric circuit, you have resistors, capacitors, inductors, and then other electronic components that we don't look at in this class. That would be in the follow-on course, which is EE 321. Okay, electronics would be different from electric circuit. So we have sources and we have loads. RLC, at this point, I'm just assuming that everybody knows what it stands for. R stands for resistor, L stands for inductor, C stands for capacitor. Okay. So R stands for resistor, inductor, and capacitor. And again, when we get to chapter 3, where we study inductors and capacitors, I'll go in depth over each and every quantity. But for now, just understand that a typical electric circuit is made up of a source and a load. A source is anything that supplies energy. A load is anything that receives energy. Okay, so source which supplies energy is known as an active component. It is still a component of the circuit, but it is known as an active component. Okay, it's an active component. It supplies energy. R, L, and C are all passive. They receive energy. They are passive. So with regards to this class, EE 201, when I say active component, I'm referring to a source. Okay, passive components are RLC, which receive the energy. Sources are of two kinds. We have a voltage source and a current source. Okay, both of those are noted with a circle. A circle means a circle with a circle with a plus minus or an arrow inside means it's a current or a voltage source. Okay. Now, in real life, those two always go hand in hand. You can never have voltage without current, and you can never have current without voltage. Okay. So a voltage source will supply voltage and supply current, and a current source will also supply current and supply voltage. So then the question is, what is the difference between the two, right? A voltage source will supply constant voltage, and it will vary the current according to the load requirements. Okay, in real life, a voltage and a current source is the exact same thing. It's the same box. If you're taking the lab and you operated a power supply, that power supply can work both as a voltage source and a current source. If the voltage is set as constant, then it's a voltage source, or the function of that power supply unit is as a voltage source. If we set the current to be constant, then it is functioning as a current source. Okay, so a current source basically supplies a constant value of current, and voltage can be variable depending on the requirements of the load. Okay, so if the power supply runs in constant voltage mode, it's a voltage source. If it's in constant current mode, it's a current source. The circle also notes that it is an independent source. And if it's a diamond, it notes it is a dependent source. Dependent sources are theoretical concepts, and there are also real life examples, but we use those for circuit analysis when we need to model complicated devices. Okay, complicated devices. So again, independent sources are noted by a circle. Dependent sources are noted with a diamond. The difference between the two is that an independent source does not depend on any external variables or external factors to supply its rated voltage or current, whereas a dependent source depends on some other part of the circuit to supply its rated voltage or current. Okay, it's as the name suggests, a dependent source depends on something else. Now, again, that goes deep into theoretical circuit analysis. It is not something that I usually or typically do in my 201 classes. At the end of the quarter, if there is time remaining, that's when I would actually involve some problems using dependent sources. But for now, the only source we'll work with for circuit analysis are independent sources. Okay. If you have a plus and a minus sign inside, it typically notes it's a voltage source. If you have an arrow, the arrow notes the current, and the plus and minus sign notes the voltage. So that's how you would know. The circle identifies that it's an independent source. Plus and a minus sign indicates it's a voltage source, and an arrow indicates it's a current source. Okay, arrow obviously points in the direction of the current. And for a voltage source, if it's supplying energy, current always flows from anybody? Which direction does the current flow for a source? It goes up. Well, in this case, it goes up, but it goes from minus to plus. So if you have a voltage source, the minus plus this way, the current is going from minus to plus in that direction. If it's listed like this, then the current is flowing towards the right. So typically current always flows from high to low. Like any other physical quantity, temperature always goes from high to low. Pressure always goes from high to low. You might have heard weather forecast, which says it's a low pressure area. So, we're going to have rain coming in. Well, current also follows the same natural pathway. Always goes from high to low. So if there's a higher potential at one end of the circuit and a lower potential at another point of the circuit, current will be going from that higher potential to that lower potential, except when it's a source. For a source, because it is supplying energy, the current direction we note is going from minus to plus. For all other components, all passive components, for resistors, capacitors, inductors, it always goes from high to low, from plus to minus. So this is true for a source, and for a passive component, which actually we'll look at, current goes from high to low, meaning plus to minus. And we'll see examples in just a few slides. I don't have a particular talk about this. I just find it funny. It's because everything just lines up. Thor is here to help you understand circuit analysis. I'll talk about prefixes perhaps next week, not right now. Okay, so we like to use fluid flow analogy to explain how a current moves through a conductor. There are some components that we have in electrical engineering that could be analogous to its mechanical equivalent, like a physical equivalent, right? And so we like to say that the conductor or circuit element can be referred to as a pipe that is conducting some fluid. And the electrons, the current flowing through this conductor can be analogous to a fluid. And then we have the concept of an electrical switch, which is noted with this symbol. This is the symbol for a switch. A mechanical valve, and this is probably just a very crude illustration. Well, not crude, but like a rough illustration, where the valve is blocking the pathway of that pipe. So electrical switch can be analogous to a mechanical valve, but the terms that we use will be completely opposite. Right now, if you look at that switch illustration, do you think that switch is open or is it closed? Any thoughts? There's no penalty for speaking up. Open, right? So it is indeed open, okay? Whereas the valve, we would say, is closed. So the terms are flipped. Okay, the terms are flipped. Electrons always need a pathway to flow. Electric current needs a closed pathway to flow through a circuit. If the pathway is broken or if it's open, if there's a break in the line, current cannot flow through. Whereas for a mechanical fluid conduction, you need an open pathway. Does that make sense? Right? For an electrical circuit, if the conductor is open, if the pathway is broken, current cannot flow through. Whereas for a mechanical pipe, you need the pathway to be open. And so the terms of the words in the English language is actually flipped. So when a switch is open, current cannot flow through. No current flow. Whereas a valve is closed, will not allow any current to flow, or any fluid to flow through. Conversely, if the switch is closed, shown by this illustration here, current will flow through. And a valve, when open, will permit fluid flow. And so the terms are flipped. Okay. This concept of switching or the switch illustrations, we will look at in chapter 4. We will actually use those to actually mimic the switching action of a solid state electronic device. Okay, just for illustration purposes, not a physical switch, but is to illustrate a point in time when a circuit changes. Okay, so the circuit would change depending on whether the switch is open or whether the switch is closed. Does everybody understand this? This is also part of your homework questions. Okay, it is part of homework, I believe 4 or 5. All right, so when we begin circuit analysis, we have no idea of the voltages or currents that could appear in the circuit, right? So we make assumptions. The assumptions are based on certain rules. They are based on logic. Okay, we assign values arbitrarily, meaning we assign voltage polarities and current directions arbitrarily. Now, when we make assumptions, as I said, we make those assumptions based on certain rules, based on certain logic. For example, we just spoke about the source, right? A source, a voltage source or a current source will have current direction and a voltage polarity. So if it already has voltage polarity, we know which direction the current would flow for a source. So for instance, if element A here was a source, we at least know the polarity of that voltage source. Then we can assume that the current flowing to that source is going in this direction. So this would be given to us, and this current direction would be the assumption. So we'd make the assumption, but the assumption would be based on certain rules. Does that make sense? So we apply or we assign values arbitrarily, right? But that assumptions, again, that arbitrary assumptions are based on certain rules and based on certain logic. So at the beginning of our analysis, when an engineer, decides to design a circuit, perhaps they are testing something, perhaps they are designing some new part of a circuit, and you begin the circuit analysis with certain assumptions. These are those assumptions. So when you decide to, when you are solving a problem, you might not be given everything in that problem. So it is your job as an engineer to actually look at the information, look at the problem statement, and extract as much information as you can. In electrical engineering, a lot of the information is in the circuit diagram. So the diagram that represents the circuit is known as a circuit diagram, and a lot of the information is embedded inside that circuit diagram. So for instance, if we just look at this as standalone, we don't know what these components are. We don't know what 1, 2, 3, 4, 5 represent. We have absolutely no idea what these mean. The only thing that's given to us in the circuit diagram are the voltage notations and the polarity of these voltages. So based on those, we can assume that the current is going or flowing in this direction. Those are the assumptions we can make. Does that make sense? Yes. We don't know. We don't know, right? This is again an example that I'm just using to illustrate, again, that everything is an unknown, but the only thing that is given to us are basically voltage polarities in the bottom figure and the current directions in the top figure, right? And so then at this point, we are not doing any analysis on this. But the information given to us, we can only assume current directions. We cannot do anything else. Yes. So, homework. Mm-hmm. That depends on whether it's supplying energy or receiving energy. So again, it keeps nagging it on the corner. Yeah, that depends. And again, sometimes when you're performing analysis, again, you have to understand that the initial problems in the homework, we are not solving for anything except, like if it's a KVL problem, you only are interested in solving for the voltages around that loop. And so no other further information is actually needed. So that's probably the case. Okay. So again, at the beginning of circuit analysis, we just arbitrarily assume current directions and voltage polarities and then begin our analysis. Now, it may turn out that at the end of our analysis, the answer for a voltage or current might end up being negative. Does that mean that your answer is incorrect? No. It just means that the actual voltage or current is flipped. As long as the magnitude is correct, along with your assumed polarity and your sign, your answers are correct, you will still receive full credit. Okay? That's all that matters. So reference directions, we use the two subscript notation for current and for voltages. So for current direction, if I use a two subscript notation like this, it simply means the current is flowing from, as it shows in the illustration, from the first subscript to the second one. So in this case, on the left, we say IAB. IAB, the first subscript is A, the second one is B, means the current that is referring to is going from point A to point B. So in this case, A would be positive and B is negative. A practical explanation would be you would take your current measurement meter or an ammeter, you take the positive terminal of your meter and you put it at the first point and the negative terminal of the meter and put it at the second point. That's what it means. IAB means you're measuring the current flowing from A to B. So the positive terminal of your meter should be at A, the negative should be at B. Is that clear to everyone? The same thing for the voltage, which is on the next slide. Okay, it just points current going from A to B. And then same thing for IBA. IBA means my measurement is from B to A terminals. Mathematically, I can write IAB is equal to minus IBA, or IBA is equal to minus IAB. You would take these measurements and it might turn out that one of those would be actually negative, right? You simply flip the terminal signs. And same thing for the voltage. So for the voltage, we have VAB or VBA. It notes that you're measuring the voltage at A with your reference at B. Meaning you're taking your meter, you're putting the positive terminal of the meter and connecting to point A, negative terminal, which is your base for reference, is at B. And VBA is the opposite. You're flipping the terminals. You're measuring the voltage at B with your reference at A. And of course, it will turn out that VAB is minus VBA. We can also write VBA is minus VAB. Mathematically, it would balance out. Important to understand that the polarity of the voltage simply tells you which end of that voltage is higher than the other one, right? Remember that simple illustration I made. If 2 points are at the same level, then the voltage between those 2 points is exactly equal to 0. One other notations we use is basically if you have a resistor like this, you would simply write down VAB, or simply if it's component R1, you would write VR1 and we would point 2 arrows at either end with a sign like this. There are multiple ways of noting voltages and currents. Specifically, voltages can be noted in many different ways. Sometimes there are no arrows, simply the voltage, either the value or the notation, and there'll be a plus and a minus sign across those notations. If you have a single-headed arrow like this, the arrow head points towards the positive polarity. So it'd be plus here and minus here. Okay. Question? Yeah. Go ahead. It is minus. Are you talking about these? Oh, positive reference. All right. at the head of the arrow. So then let's come to that homework. That homework problem was describing, let's say it was describing VAB. It had 4 points in a circuit, A, B, C, D, right? A, B, C, D. And for homework problems like this, it always helps to draw it out. So let's say we have a 2D illustration, and this is 0 volts, right? It's a 2D graph. VAB was given to us as, think, well, whatever it might be. Let's say it was 5 volts, right? So now that you know what two subscript notation is, which point of VAB is higher? A is higher. By how much? By 5 volts, right? So let's randomly put down B somewhere here and A somewhere here. Then we had, what do we have? VCB or VBC or something. I can't remember what it was, but let's say it was VCB, and VCB, let's stick to 10 volts. So then which point is higher, C or B? C is higher. By how much? 10. And what is the common voltage between the two? B is common between both, right? And this is not to scale. So let's say this is 5 volts between the two, and this is 10 volts between the two, right? So B is common between both. So now what is the voltage between A and C? 5, right? So VAC is, magnitude is 5, but I said VAC, and A is lower than C. So it'd be -5. So VCA, we can conclude from here, VCA is 5 volts, but if it's asking VAC, it would be -5 volts. So it always helps to draw it out, okay? When you have problems like these, not just for electrical engineering, even in your own fields, it always helps to draw it out. And then there was another, I think there was a third voltage, VCD or VAD or something. But again, you get the idea of how you need to plot it, right? So if you lost points on this problem, you send me an email. Now that you have this information, you go ahead and solve it. And then I will adjust your credit if you lost points, okay? All right, any questions? Okay. Then memes about Ohm's law. George Ohm was a physicist who did a lot of research. Well, actually, a lot of people do a lot of research in the same area. It just happens by good fortune. You know, one or two people end up being, you know, more associated with a particular topic, and then, well, then the thing gets named after them. So George Ohm was one of the researchers who was working on, you know, currents, voltages, resistances, and so they came up with this law, electrical law, and that law came to be known after them. Okay, simply stated, Ohm's law states that voltage through a voltage across a resistor is a product of the current flowing through it, a product of the resistor and the current flowing through it. So anytime current flows through a resistance, it encounters resistance. It causes a drop in the voltage across its two terminals. The point of entry is higher, the point of exit is lower. So the electric potential difference between the 2 points results in a voltage across those terminals. And because it's a drop in the voltage, it's also sometimes referred to as a voltage drop. Okay, so a resistor is symbolized by this zigzag jagged symbol. And you have a current flowing through that resistor with a value of I. It causes a voltage drop. The point of entry is minus or plus? Anyone? No one? There are some murmurings. It's plus. I just said For a passive component, current always goes from high to low. So if you know the direction of the current, you can assume the polarity of the voltage. If you're given the polarity of the voltage, you can assume the direction of the current. Okay. Now, all of these concepts and topics, they are fundamental topics. I try to cover all of these in my classes because it, again, going back to the same reason, it may be a while since students have done these prereq classes, but these are fundamental understanding principles, fundamental principles to understand. If students do not get these concepts, they will have a hard time doing circuit analysis. Okay. Questions? There were some questions. Yes. Is it homework 3? Yeah, we'll get to it. Power and energy, right? Yeah, we'll get to it. So Ohm's law, this is the most fundamental of laws. You can pretty much solve all circuits using Ohm's law. Well, actually, let me put it this way. You cannot solve any circuit without Ohm's law. Okay, V equals IR. You can use any mnemonic you want with it, but V equals IR. That is the most important equation that you would use for electric circuit analysis. Okay, everything else flows from this. When current flows through a resistor, energy is transferred. Energy is transferred to that resistor. Resistor, as the name suggests, resists the flow of current. Later on, we will encounter the term reactance and impedance. All three of them are kind of synonymous. They are all synonyms of each other. You have resistance, reactance, and impedance. Impede, right? It's opposing. It's opposing something. And we will see that in chapter 4. Not chapter 4, sorry, chapter 5, AC analysis. But when energy is transferred to a resistor, what happens to it? Electrical energy is being transferred, right? Generates heat. So resistors dissipate the energy as heat. Okay, it opposes the flow of current. It dissipates the energy as heat. And that's why if you're running a high current appliance like an electric heater, they will always give you a warning. Do not use an extension cable with that electric heater. It's because when current travels through a piece of wire, through a piece of conductor, that conductor will have some resistance. The higher the amount of current, the more energy that is being transferred, the more heat that is being dissipated, the more heat that is being lost. So if you use an extension cable with an electric heater, it needs to be really thick and be capable of carrying that amount of current. Otherwise, that wire gets hot. Chances are it'll blow out and will short circuit and blow out your fuse. So you can use extensions with your electric heater. They just need to be, strong enough to actually withstand the current requirements of that electric heater, which most people will never look at the power rating of an electrical extension cable, right? That's why all electric heaters will come with a warning. Do not use an extension cable. Fire hazard. Yes. It doesn't matter what it is actually. So, yeah. This is just an illustration just to show what it is. We don't actually know what it is. We don't actually care because it actually does not matter. So in this case, coming back to the slide, when current flows through a circuit, voltage appears across that element. If there's a voltage across an element, current would flow to that element. Okay. Energy is transferred. The rate of transfer of energy is the power. It's given by the power equation P equals VI. Electrical power is the product of the voltage and the current for that component. Okay. So power associated with a component is the product of the voltage and the current for that component. Now, if the voltage and the current polarity are the same, meaning in the same direction, So current is entering the positive terminal of that component. Then the power is said to be positive. Power is said to be positive. The equation you would use would be P equal to plus VI, or P equals VI. The plus is implied. If the current is entering the terminal from the negative end, if the current is entering from the negative end, then you remember the point of entry for a current reference direction is positive, right? So if it's going in the upwards direction, current has positive at the tail end. So if current is entering the negative end of the voltage polarity, then the power is negative, energy is being supplied by that element. So to answer your question, we don't know whether it's a source, we don't know whether it's a load. In this case, it's just an example to show it could be either. It's unknown to us. It's for us to figure out. So if we have the voltage polarity and we have the current direction, we can assume that the power is either positive or the power is negative. So here, power is positive. Here, the power is negative. So energy is being received or energy is being absorbed when the power is positive. When the power is negative, energy is being supplied or energy is being lost. Okay. So again, if current enters the positive terminal, power is positive. If current enters the negative terminal, power is negative. Okay, it's also known as the passive reference configuration. Okay, when the current and the voltage are in the same direction, meaning for passive components, it's always in the same direction, right? Passive components, current flows from plus to minus. So current is entering the positive terminal. If current enters the positive terminal, power is positive. So you would use the equation P equals to VI. Again, simply stated, power is positive. If current enters the negative terminal, power is negative. You would use the equation P equals minus VI. Okay, in both cases here, this is plus, this is minus. And here, you would simply extend the arrow. Current is still entering the positive terminal of the voltage. Here, if we extend the arrow, current is entering the negative terminal. And here again, it's entering the negative terminal. Okay. So again, passive reference configuration. If current enters the positive terminal of the voltage of that component, power is positive. If current enters the negative terminal, power is negative. If power is negative, it is supplying energy, it is supplying power. So it is a source. If power is being received, it's a load. A real life example of something that can act as both is your mobile batteries. Your smartphones, your tablets, your laptops. When you plug it into the wall and the battery charges, the battery is acting as a load. It is receiving the energy. So battery is being charged, it receives the energy. Power associated for that battery is positive. When you unplug it from the charger and you use the battery to power your devices, the battery is now acting as a source. So now the power associated with that battery is negative. So rechargeable battery is both a source and a load, depending on your usage. Make sense? So let's look at some examples for power. We have three components, A, B, and C. We are given the voltage polarities. We are given the current directions. We are also given the values for each. We simply decide which equation we need to use. We plug in the values and we obtain our final answer that will decide whether power is being received or supplied. So in A, my current is coming down from the top and the terminal is positive. So what is my power equation? plus VI or minus VI? Plus VI. This would simply be 12 times 2, 24. How many for joules? How many for watts? So power is always watts, energy is joules. Again, we are all here to learn. So if you speak up and you think that you're wrong, don't feel embarrassed or don't feel that I'm going to deduct any points, right? I enjoy participation. So 24 watts. Named after James Watt. All right, for 2. So not 2, sorry, B. Example B, we have current entering the positive or negative terminal. Look at the arrowhead. So if you extend the arrow, it's entering the negative terminal. Okay, so negative terminal. So equation we would use is minus VI, negative VI. So minus 12 times 1, minus 12 watts. You do not flip it twice, okay? Which is the example C. So in example C, if we extend the arrow is going or entering the positive terminal, right? It enters the positive terminal. When you plug in the value, so positive terminal means you use the equation, positive power equation, which is plus VI, and then you plug in the values that are given to you. So it's 12 times minus 3 gives you minus 36 watts. The end result, now you look at the end result for all 3 of them. Here, power is positive, right? The final answer is positive, meaning the energy is, it's being received, right? It's being received. So energy is either received or absorbed. Here, the power is negative. So energy is being supplied. Here again, final answer is negative. So energy is being supplied. Do not solely look at the power equation. Here we have, in example C, we have a positive power equation, but that does not mean it's positive power. Okay, again, that's specifically why I chose this example, just to illustrate the point that the values could be anything. Make sense? Now, let's see. So KVL, KCL is done. All right, let's take a pause, think over all of this information. Let me know if you have any questions. Any questions at all? So it's a lot of information. You have to sit and reflect. Yes. So it's 2 ways. So if it's a source that is given to us, then we know it is going from minus to plus. The flip side of that is if we see a circuit and a current voltage polarity and current direction is given to us, then we can deduct from that, or we can conclude that that thing or that component is a source. Okay. Right. Any other questions? So how many of you are familiar with this? Flat line and an alternating line. Most have seen it in physics, hopefully. This is simply a 2-dimensional graph representation of the plot of either a voltage or a current. It could be for voltage, current, power, energy, doesn't really matter. Let's just say it's voltage and current. It could be V or I or power. X-axis is always time. X-axis is always time. Left side is 0. That's the beginning point. 0 does not mean the beginning of time. I don't think that'd be a large philosophical discussion. 0 time t equals 0 simply means the point in time at which we begin our analysis. That's all it means. Okay, so this would be t equals 0, and here it would be I equals 0. If the value of that quantity remains constant with respect to time, we refer to it as DC, direct current. The C in DC and AC stands for current, but ignore that. We simply use the acronym DC and AC. Otherwise, it sounds weird. Like if you expand that acronym, it's DC current, and AC alternating current. But it's DC and AC, so it's AC and DC voltage, AC and DC power, AC and DC current. Okay, AC and DC circuits. Oh, circuits, by the way, the thing that makes them AC or DC is the source. The components are the same: resistors, capacitors, inductors, but the source, whether it's the source is DC or AC, makes the circuit AC or DC. Okay, so that's A. In B, so this is known as direct. This is known as alternating, because the value of that quantity is not fixed. The value of that quantity alternates with respect to time. And when we refer to AC, it does not mean it's always alternating. It means that the value is not fixed with respect to time. It could be anything, does not have to be alternating, meaning it could be something like this, be something like this. It could be random noise signals. All of it is classified as AC. If it's not fixed with respect to time, it's AC. So now I would ask you the question. This is kind of in the border between a general knowledge question and a specialized engineering question. What is our power outlet? Is it DC or is it AC? It is AC. But every device, every component that we use in modern world is all runs on DC. Everything that we look, that's why we have the adapters and the chargers that we plug into the walls. What that adapter or the charger is doing is converting the AC wall outlet voltage into a DC. So anytime you look at any charger or adapter, it will have the input rating and it will have the output rating. So next time you have a few minutes, you take a look at your chargers and your adapters, it'll tell you the input voltage rating. That input voltage rating tells you it's valid for 100-240 volts. You can use it anywhere in the world, which is what most chargers are nowadays. You can use them anywhere in the world. And then one final thing I want to talk about today is unit prefixes. I expect each and every student to memorize this entire table because it's going to appear on the final exam. No, not really. Even I don't have this table memorized. Okay, I don't expect students to memorize this table. Most of you are familiar with the center of the table. You have kilo, mega, giga, tera, and then micro, nano, milli, right? I'll give an example of both on both sides. Let's look at the tiny. So the reason we use unit prefixes is because in engineering, we deal with values that are extremely small or extremely large. This is not just for electrical engineering. You use this in everyday life. You use this in your own fields, right? Cordless phones, wireless, Wi-Fi routers. This is a frequency band, 2.4 gigahertz, 5 gigahertz. A few years ago, FCC opened up the frequency spectrum of 2.4 gigahertz for consumer use. So cordless phones used to run on that frequency. Microwaves run on that frequency. Wireless routers run on that frequency. Became so crowded that they opened up a 5 gigahertz band. So all wireless routers also now use 2.4 and 5 gigahertz. Giga, 10⁹, huge amount, right? So on this side, you have milli, micro, and nano, right? Now those terms are like pervasive in everyday life. You know how small a micro is? I mean, mathematically we know, right? You know how small a millimeter is, right? Millimeter, everybody's seen that millimeter. If you take that millimeter and divide it into 1,000 parts, That is 1 micron. A human hair, by comparison, which I don't have a lot left anyway, but a human hair is on the order of about 70 to 80 microns. 1 micron, by the way, is 1 micrometer. That's where the word microchip comes from, because the early microchips were built on the order of micrometers. Okay. If you take 1 micrometer, 1 micron, divided into further 1,000 parts, that is 1 nanometer. It's that tiny. On the other side, we have kilo, mega, giga, and tera. I'll ask you a guess on how much is 1 million seconds. How much is 1 million, by the way? 10 raised to 6. How much is 1 million seconds? Quick guess, wild guess. It's about a few days. It's less than 12 days. How much is 1 billion seconds? That's the difference between a billionaire and a millionaire. All right, on that note, I will bid you all a good weekend. I will see you all on Monday. Quiz on Monday, do not forget. Every Monday we'll have a quiz. I will post an announcement sometime later this evening. It will be based on the material that we have covered this week. Okay, so material from these 2 classes and homeworks 1 through 5.